Alright, here are the next couple examples. We're going to connect what we've done algebraically with average velocity and instantaneous velocity to its geometric or graphical representations. Alright, so in exploration 1 here, we're looking at figure 10.1, and it wants us to connect the points 1, 1, and 2, 4. Alright, now this is called a secant line because it connects 2 points on the curve. Now, in part 1, it says find the slope of this line. So remember that slope equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So it's going to give us 4 minus 1 over 2 minus 1. So that's going to be 3. Now in part 2 it says now find the average velocity of the ball over the time interval 1 to 2 seconds. So velocity average, that's our change in s over our change in t. Well, our change in t is 2 minus 1. Our change in s, so at 2 seconds how far is the what's the distance traveled? That's 4. Minus, at 1 second, the distance traveled is 1. So we're going to get 3 again. So in part 3, what's the relationship between the numbers that answer 1 and 2? They're the same. In 4, it says in general, how could you represent the average velocity of the ball over the time interval a comma b geometrically? Alright, so to answer that we're going to need a little bit more space, and what we're going to say is that average velocity is the slope of the line connecting, that's a C, the 2 points. Or the secant line. Okay, so if we were given a graph and we had to find the average velocity, what we would do over a certain interval, we would plot the points on the graph, connect it with a line, and then approximate the slope. So that slope would be an approximate for average velocity. Okay, example 3, it says use limits to find the slope of the tangent line to the graph of s equaling t squared at the point 1, 1. And again, you can look at figure 10.2 to see that, what that looks like. Now, the solution to this will look a lot like the solution to example 2. So we want to take the limit as t approaches 1. So we want to look at the interval from 1 to t. So our change of s over a change in t equals the limit as t approaches 1. Now our change in s, what we have to do is take t, plug it in to our equation, so you're going to get t squared. Take 1, plug it in, So t squared minus 1 squared, and then divide by t minus 1. Alright, we cannot plug in 1 for t right now because we'd be dividing by 0. So we want to look to simplify. So the top is going to be t squared minus 1. That's a difference of squares. So you're going to rewrite that as t plus 1 times t minus 1 all over t minus 1. The t minus 1's cancel, so you have the limit as t approaches 1 of t plus 1. Alright, now we're in a position to plug in 1 for t and get 2. Alright, so the slope of the tangent line to the graph of s equaling t squared is 2. Let's go back and confirm that. Alright, so here's the point, 1, 1. If I draw the tangent line, it's a little too steep. That's better. Okay, so the tangent line intersects the graph at 1, 1 at only that point. So you can see that I'd have to go up to, the slope is going to be up to over 1. So the slope would be 2. Alright. Alright, so if you compare example 3 here to example 2, it should be apparent that the method for solving the tangent line problem can be used to, it was the same thing that we used to solve the instantaneous velocity problem in 2. So this is important. Alright, make sure you copy this down. Instantaneous velocity, alright, is the slope of the tangent line. So if you were given the graph and you had to find the instantaneous velocity, you would draw a tangent line and find the slope of that tangent line.